tape rolling.
Alright, so, is recording?
Yeah.
Yes.
Hello, period 4, and my many, many fans on the internet. The conics unit is over, but it's not really over because it's never over, because conics, woo! So let's do some fun things for 10 minutes, and then I'm going to do one big awesome thing that just like wraps it all up and makes it all make sense to you. One thing that we never did, but was like on my plan to do a long time ago, was construct the, watch this. Da, 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 and da, da, and da, da, da. Alright, can I do this? Yeah, I can. Ready? I'm gonna make an ellipse. Sound a little bit like impressed or something. Okay, let's go. I'm gonna make an ellipse. How do you make an ellipse? Well, you first construct the foci. And let's see, I'll call this point like, whew, I'm a focus. No, let's call it just like F1 or something. F1. Get some caps in there. What's up? F1. Woo! And then we have this other point, F2. Woo! Okay, and now what do we need? Now I need a string, yeah?
Yeah.
Okay, well for that I shall construct this auxiliary line, which I will make horizontal. It's auxiliary, so we can make it thin. What are you guys talking about over there? Good, hide it so it never gets unhorizontal. So this is like my helper line. Okay, now I want a string. So if I want a string, but I need a particular string length, so I'll put a point here and a point here. And this will be the length of my string. Alright, well if the distance between these 2 points is the length of my string, then what's the definition of an ellipse? Well, it's going to be all the points, so the sum of the distances to the foci is that length of that string. Well, how am I going to do that? Yeah, Rajiv.
You're gonna like put the endpoints of the string on like each foci, on each focus, and you're just gonna like stretch it as much as you can and like sort of like go around.
Okay. But that's like if it was like a string, but this isn't a string. It's like that. Like I have to like construct it. Yeah.
How about you watch it?
No, I don't need to watch a tutorial. I know how. It was a rhetorical question. Thank you for that tutorial. This is the tutorial, man. Other people are watching this right now. Good. We need to. Well, what do we need to do? It's really like 2 segments, right? We need it to be the case that from F1 to some point back to F2 adds up to be the length of this string. In other words, no one gets it.
Segments and up to like an equation that says they have to like equal.
No equations. 2.
Make a triangle. Oh, and like make a point on the line.
Yeah. He said, yo, break that string up into 2 pieces.
And then we can like make a circle around.
Oh.
Yeah, so let's make this like blue, and let's make it thick, and then I'll make that also thick but like red. Alright, so in other words what I've now done is I've partitioned this string up into 2 pieces, yeah? But also it's like dynamic geometry software, so I can like drag, keeping the length of the string the same, I can drag this point around, and that splits up that string length into like many different pieces, or like two pieces in many different ways. And now I want to know all the points, which are like, say for example, a blue segment away from F1 and a red segment away from F2. Whoa, are you seeing what's going to happen now?
And then just trace.
Yeah, so we're going to do a little bit of this. So construct circle by center and radius. Let's make that circle red, because that's the red circle. And then we construct circle by center and radius and make that one blue, because that's the blue circle. And what is this circle? It's all the points which are a blue segment away from F1, and the red circle is all the points that are a red segment away from F2. And because this is dynamic geometry software, as we drag this point along the length of the string, we're considering simultaneously every possible sort of partition of that string into 2 segments. Follow? And where's the ellipse?
All those.
Behind the intersection of those 2 circles. And so you can sort of see the ellipse being made, yeah, as we drag around. Okay, and you can even do the thing that we've done before, where we trace trace intersections, and then we get a little.
Whoa!
Not 8.
Ellipse. Impressed?
Yes.
Okay, cool. It gets better even. Watch this. Let me now. What am I going to do now? Let's erase all these traces. Erase traces. And now I can construct the locus. So if I go shift advanced preferences. Yeah, that's good. Okay, good. So now we can say, yo, I select this point and this point, and we're going to construct the locus of points satisfying this point as this point moves freely. And I'll do it again with the other point of intersection, construct locus. And now I can sort of hide these circles because they're not really needed anymore. And now I just like have my ellipse just like constructed. And since this ellipse is since this is dynamic geometry software, then it will like adapt instantaneously as I like drag the foci around.
Whoa.
Oops, I dragged too far. I ruined the surprise. Yeah. If the points are really close together, then like that means the eccentricity is really, really close to 0, right?
Right.
Because like C is very tiny, but A is pretty big. And if I drag the foci far away, then now the eccentricity is very, very close to 1, right? Because now C and A are almost the same. And I can also make the string longer too, by the way, keeping the foci. If I make the string longer, then I'm increasing the length of 2A. If I make the string shorter, then I'm keeping C the same, but I'm making it bigger. Follow?
Yeah.
Okay, and then the thing that I accidentally messed up, hopefully you blinked and didn't see it. What happens if I keep pulling the foci farther and farther apart from each other?
Eccentricity reaches 1.
I can't believe I ruined this. Ah.
Just edit it out in the video.
Edit it out in the video? Yeah, good. I will. Don't know how to do that. I keep pulling and pulling now. Suddenly my eccentricity is like virtually 1. It's like 0.99. It's 0.999. Whoa! This should just blow your freaking mind. It's a hyperbola.
Whoa!
Oh my God! How it's like somehow the foci just like burst out of the ellipse and a hyperbola was created. How did that happen? Why did that happen?
Hello. Hi, Brian.
Does this convince you in some kind of like weird fundamental way that like hyperbolas and ellipses are like not even different objects? They're like literally the same object. It just depends on how far away the foci are from each other. Right now that C is bigger than A, effectively what happened, as soon as I pull the foci farther apart from each other than the length of the string is, then C is bigger than A. But actually understanding how this could happen is kind of bizarre. And I did this in a particular way. Yo.
How long is that piece of string?
Is it a real question? Okay. Good. I love when you just say things that are not helpful. All right. I just did this command called show all hidden, which reveals all
The circles.
Wait, what am I doing?
Oh,
I kind of like messed up. I meant to like rehash it.
It's
Hi. Okay, the thing that I did that was very tricky is to make the, to construct this point not on the string, but on the line. So the tricky I pulled on you is that this point is moving freely across this entire line. And so this point can be sort of like beyond the length of the string, so to speak.
Right.
And when it's beyond, the only time the reason why I get a hyperbola, and I get a hyperbola when these circles intersect. But these circles are going to intersect when the total length, right, the blue circle, the red, what am I doing? When the blue is the length from the left endpoint all the way to this free moving point. And it's when the difference in those two circles have the length of the string that I get intersections between these two circles. Bob?
Well, tracing is on it.
Alright, so that was like pretty cool. And then even by hiding the what the What just happened now?
Tracing was
I grabbed the wrong point.
You should just remove the
Erase traces, and I also want to not trace those points anymore. Oh, okay, I don't know. All right, good. So hiding these two circles, you can also, I can also move the foci farther apart from each other, and now the eccentricity is getting like bigger and bigger, right? Okay, that was pretty fun. I have a couple other like cool small little videos to show you. One is, okay, this is this thing I made when I used to teach Algebra 2, very briefly, because my students like didn't understand conics forever, so I made all these like silly examples. Actually, this is a freak out. Fido is a dog. His owners want to take him to the park, but the law says that dogs must be tied up at public parks in their city. The first week they take Fido to the park, they bring a 34-foot long rope and tie one end to Fido's collar and the other end to a stake they place in the ground, marking their favorite spot in the park. Describe the shape of the boundary of the area Fido can run around in. What's it going to be? A circle. Woo, of course. Now, second week, Fido's owners, this is not even that like cool or anything, because it's like duh. The second week, Fido's owners decide to get more creative. They bring Fido to the park with the same 34-foot long rope, but this time they bring two stakes. They slide the rope through a ring attached to Fido's collar so that he can run along the length of the rope. Get it?
Yeah.
Then they tie each end of the rope to a stake and place the stakes on the ground 30 feet apart from each other. What is going to happen now? An ellipse. And I did this. Woo! Here is Fido. Here are the stakes. Here is the length of Fido's rope. And we can drag this point and we can make Fido run back and forth along the length of the rope. And you can even click a button that says, "Run, Fido!" And it will, man, I've gotten so much better at Sketchpad since I made this. Also, like, I'm like old, so Sketchpad was like, when I used to be like the young cool teacher that was like 27, I like had technical skills, but like now all I can do is this stupid crap like Sketchpad, like real useful things, like I don't know how to do. We need the young people to teach me. Alright, also I can click on this and it will show the boundary as the points get traced around. Cool? And indeed it's an ellipse. Alright, that's impressive, but it gets better. Alright, now, here's a story. The residents of Alphaville and Betaville have a problem. They love to run long distances and they love to race, but everyone in both towns runs at exactly the same speed, a mile in 8 minutes. They used to try to have races from one town to the other, but it was always a tie. Silly Alphaville and Betaville, you all run at the exact same speed, so every race is a tie. What are they going to do? Well, the mayor of Alphaville, Mr. M, proposes a new plan for 2006, the Great Ellipse Race. What they now do is they will start the race in Alphaville and end it in Betaville, but they will paint a giant ellipse through the countryside, and now there's like a skill component to the race. What you have to do now is each runner must run from Alphaville, tag the ellipse, and finish in Betaville. The skill is to figure out which point on the ellipse to run to so you can finish the race first. Uh-oh! What happens?
It doesn't.
It's still going to be a tie because the sum of the distances to the foci is constant for any point on the ellipse. Get it? That was like a joke. Here we go. Should we do it?
Yeah.
This is my life's work right here. Begin. Here they go. They're all running. Oh, look. R is definitely going to win. It's a tie. Let's try it again. Here we go. R, what are you doing? You're going backwards. Wait, no, I changed my mind. Now you're going to win. Why? You're going to clearly be last. It's a tie again. Okay, surely this time someone is going to win. N, you're doing really well. S is never going to catch up to you. Wait, no, I changed my mind. No, it's a tie. This is cool. State-of-the-art graphics. Do you notice it's randomizing every time?
Yeah.
I constructed it to randomize. The whole thing, it plays eight times. Woo! Sum of the distances to the foci constant. So beautiful. So beautiful. Woo! Okay, good. I even have like a couple more that are even more silly. Wait, when does the period end?
I don't know.
Let's
Does anyone know exactly?
Yes.
There's one more thing, which is, oh, this one. This one's kind of dumb, but it's kind of cool. Billy and Emily want to have a foot race. They've noticed, I don't think they've time. When is the period end? 20 minutes, that's all? 20 or 30 is not really the kind of precision I'm looking for.
It ends at 11:09.
Oh,
Yeah, 11:09.
11:09. Okay, we can waste like 3 more minutes. All right, Billy and Emily want to have a foot race. They both run at the same speed, but Billy has better endurance. So they decide it would be fair if he has to run 2 miles longer than she does. He should get a head start, and when he's run 2 miles, she should begin. Billy wants the race to start at his house, but Emily wants the race to start at her house. They compromise that each will start at his or her own house and run to the finish line along separate paths. Their houses are, blah blah, 5.2 miles apart. They can't decide, however, how long to make the race. So what can they do? Oh, they need to find the locus of points that are 2 miles longer, farther from Billy's house than they are from Emily's house. Get it? This is like pretty big. But anyway, here it is. Woo! So this is the length Emily has to run. This is the length Billy has to run, and these are like they're like a little bit farther, right? So the race would end here if Billy runs 2 miles longer than Emily, but they can also make the race shorter. And so as how do I do this? I don't remember. So now so Billy says no. Emily says what's going on? Oh, they're compromising about where to make the race. Billy wants to make the race shorter. Emily wants to make it longer. So when you click the button, it goes back in the other direction. Get it? Whoa. And what you get is a hyperbola. Is the locus of points that are 2 miles farther from Billy's house than they are from Emily's house. It's the possible locations of the endpoint of their race. Get it?
Yeah.
Okay. And then I even have a silly one for parabolas. There's like a river and there's like a tree and you like hide your food in a tree or something and then you go on a hike but you have no pockets, so then you might get hungry or you might get thirsty. So you want to stay equally far away from the river and the tree at all times. So based on whether you get hungry or thirsty first, you'll have the same amount of distance to go back and take a drink from the river, which is something that we do all the time. So here we go. Let's go exploring. Oh, it's not working. Yeah, it's working. Oh yeah, I think I have to add traces. Show traces. Woo!
Like disappear and something.
Yeah. And so woo! And now, wait, this is the good part. I'm feeling a little bit hungry or maybe thirsty. Then we run back. Boom! Hitting at the same time. Did you see that?
Yeah.
That was supposedly impressive. Watch. I'm feeling a little bit hungry and thirsty.
Whoa!
So you head back. Woo!
Oh.
Thirsty, hungry. Yeah, I know. This is an argument for
Cargo.
cargo pants. Yeah, good. All right. Whoa. Good. No, I don't want to save all the stuff. All right, good. That was like pretty exciting. There's even like more crap on here. But maybe do we want to see more things or no?
Yeah.
I think there's like some kind of construction of a what is this?
Leave a like and subscribe.
Oh, this is like a whole nother way to construct a hyperbola.
Whoa.
Oh, it's like the intersection of points when you rotate. Okay.
Whoa.
I'm not even totally sure what's going on.
I'm not either.
What's going on?
The hyperbola itself is the intersection of a point. Okay, they're given a point out here, this one, and given a circle of a certain radius. Bless you. Connecting the segment from that point to the point going around the circle, and it's the intersection of the perpendicular bisector of that segment and something else. And the ray through the rotating point in the center. Oh yeah. What else? This is another beautiful thing. I don't remember how it works though.
Good.
I think I have to do something. At this point? No.
No.
This point could be better before it works. I don't remember how this goes. When I thought I had one, oh yeah, here we go. This is the parametric equations of the ellipse.
Whoa. Oh.
This is like literally constructing the ellipse by constructing A cosine theta and B sine theta. If you actually like slow this down a little bit, you can follow what's going on.
Looks like Saturn.
Should we pause? Pause. This point on the ellipse is the point of intersection of the cosine of this little
Where's the sign?
circle, or the sine? Yeah, it's the sine. Yeah, it's the height as we roll around this circle, and it's the intersection of the x-coordinate of the cosine of the big circle. Whoa. So I basically just constructed two circles, of sides of radii A and B, constructed the sine of one, the cosine of the other, and just plotted those points x comma y. Follow?
All of them.
Whoa. And then I did this with hyperbola too, I think, somewhere, but I don't remember. Oh, here it is. This one's like harder.
Whoa.
We don't have time to analyze this.
Whoa.
Alright, good. That was like fun. Now a math thing. Ready? I'm going to answer, finally now, every single possible question that you ever might have had about 19 minutes. Perfect. About the conic sections. And look, man, we did a lot of awesome things. We like went beyond the national. I'm going to go do it. Well, I guess I can do it here. I'm going to go. We went beyond the kind of like standard national curriculum on conic sections. Like really pretty far, man. In fact, we did a lot of really good things, such as we introduced the geometric definition of the conics, and we proved, and we introduced the two focus definition, and then we proved that they were equivalent via Dandelin spheres, yeah? Then that gave an answer to the question, like, what really are foci? In the standard treatment of the conic sections, in which you just sort of say, hey, take 2 points, make a string, then you're like, what are foci? They're just these 2 points. Well, we now know actually like what foci are. What are they, like really, geometrically?
They intersect the Dandelin spheres.
Yeah.
They're the points of tangency of the Dandelin spheres with the intersecting plane of the cone, right? And we then took a whole new definition, the definition which which takes as primitive a focus and a directrix and an eccentricity, and we defined an ellipse as the locus of points with a constant eccentricity. And then we showed that those two definitions are equivalent to the two focus definitions. But what we didn't really answer, and one person this semester actually asked me this question, they were just like, wait, Mr. Rose, like, what like just is a directrix? What's a directrix? That's a line. Does that line have some geometric significance? Oh, and by the way, like, what is eccentricity? These are all very good questions, and we are going to answer the question right now. This depends on me having extremely good art skills, and I only make this picture about once every 2 years, so this is going to be bad. All right. So, let's go. Oh, should I answer the question first of what a directrix is? A directrix is, you can see it over here, the intersection of the intersecting plane and the plane through the circle of tangency of the Dandelin spheres.
Oh.
Can you say that again?
What is right? Can you guys move your desks like farther away from me? Good. Okay. Here comes a gigantic picture. Oh, and you might recall that like forever ago I passed out some handout to you that was like that you like looked at for like 0 seconds called like this.
Yeah.
Yeah. If you get that out, there is a picture of what I'm about to draw on it. And it's on the back, yeah. Okay, good. Alright, so I shall begin. One time ever I did this well. Every other time it ended in disaster. Let's see what will happen now. Okay, first I shall draw a cone. Can I do this? I can do this. First, I shall draw a cone. Okay, here is my cone. And it's like an infinite double cone, so it like goes on forever and stuff. It's called the vertex O, and call it like cone C and whatever. Okay, now, this cone, of course, has an axis. And so let's let the axis of this cone be line L. So line L is the axis of this cone. And also this cone has a certain vertex angle. Let alpha be the vertex. I don't think you need to get so close, but whatever.
Oh no, it's clear. Like there are a lot of people like blocking the view.
Okay, so we have cone C. It's like already looks bad.
You can do it, Mr. Rose.
Thank you. Good. So cone C, vertex O, axis L, vertex angle alpha. All right, and now there is a intersecting plane pi, and this intersecting plane pi is going to come in all like so. But I'm actually going to draw that not next. First, I'm going to. Well, I guess I have to kind of. Huh? Okay, let's go. Can I do this? Probably like not.
Whoa.
So, all right, sure. Okay, this is my plane pi, and this plane pi is going to intersect, and it's going to form an ellipse. And so the ellipse is going to look kind of like this. That's kind of okay. Ellipse E. Okay. I guess it would be like touching up at the top of this thing too, huh? So that maybe that's not so good.
Draw the top line.
Just draw the top line a little lower.
No, just draw it through the ellipse. No, not
Like a
through the
dotted
cone.
line.
Through the dotted
What's up?
line. Just a dotted line through the cone instead of just leaving this.
Sure. Okay. Good. All right. Ellipse E. Oh man. Woo. Good. Now, what next? Now I shall draw the lower dandelion sphere. What's up? No, I'm not stepping anywhere. You move your camera. I'm the movie star. You deal with this. Good. So then there is a lower. There is a lower dandelion sphere, and the lower dandelion sphere is going to intersect the plane at point. How's that? Oh, this is just a disaster. Okay, hold on. No. It's all wrong. All right. Riveting video. Okay.
You should do a time lapse.
Like some whack-a-mole.
Like in a
Okay, no, I got this. Give me another non-ironic bit of encouragement. Okay.
Whoa, you can do
All right. Good. So what I really want is the circle of tangency to be like really far down here. Okay. Sure, whatever. Good. Maybe I won't even draw the bottom. Wait, don't lose it, because it's like it's. We should try to be serious. Okay, good.
What is that?
Good.
Find this video.
Okay, good. So that's the lower dandelion sphere, and this lower dandelion sphere intersects. Let's call this F2, because there's also an upper dandelion sphere, not pictured. Okay. And now, what is going to happen? Well, we have our circle of I have a list of all the things. Directricity. Oh, we have then this circle of tangency. And the circle of tangency looks like this. This circle is called C2. It's the circle of tangency of the lower Dandelion sphere. Does everyone remember this from the Dandelion sphere day?
Yeah.
Why are you laughing? Is it that bad? Okay, but is it like good enough so it's like kind of okay? It's very hard to draw.
It's okay.
Okay, now, what we're going to do is we're going to draw the intersecting, we're going to draw the plane through the plane through this circle of tangency. Okay, this is the hardest one to draw of all. My own directions of what order to do this in I have not been following. That was a bad idea, I now realize. Okay, so I think I need a new color. And I'm now going to draw this plane. I'm going to use purple. Okay, so this plane cuts through, is the plane of this circle. It's the plane perpendicular to the axis. And it comes in all, oh God. I don't know what to do.
Yeah, Mr. Rose, you can do this.
Sure.
Yeah.
Confidence.
Parallelogram needs to look like steeper, like much steeper.
No, too late.
The front should be wider.
That's fine, that's fine.
No.
What's wrong?
Make the lines parallel.
Okay, so let's call this plane, let's call, quiet. Let's call this plane, doesn't matter what we call it. Okay, but see, do you see what's happening? Is that this is the plane through that lower circle of tangency. Then there's also this plane pi. And eventually these two planes are going to meet. Alright? And so now, let's do that. Let's let these two planes meet. And they're going to meet in a line. This line is the directrix. That is what a directrix is. The directrix is, which I'll name D, is the line of intersection of, this picture looks great. Bunch of haters. This is a beautiful picture. There is this plane. I mean, it's very, very clear what's going on, I think, right? There's this plane through the lower circle of tangency, the circle of tangent of the lower Dandelion sphere, and then there's this intersecting plane which makes the ellipse. That's the directrix. Okay, what's next?
This one is good. One those bad look like.
Now, what I am going to prove, so now that I have constructed the focus and constructed the directrix, what do I have to prove what am I even doing right now? Maybe I should say that.
Eccentricity, right?
What I need to
What
do
does it really
is
mean?
show that the eccentricity is constant. Now that I have a geometrical manifestation of directrix, I am now going to prove geometrically that for an arbitrary point on this ellipse, the distance to the focus over the distance to the directrix is constant. Which is and we're going to actually know what eccentricity is, really, based on the cone model. Okay, so now I will choose an arbitrary point P on the